Hello, welcome to Memory in the Age of AI Agents. What we are covering today, it isn't a feature, it's not an optimization. It is rather single most important architectural frontier in the modern AI. The ability for an agent to remember across time, improve from experience, and at the same time maintain a sense of self is what separates a useful tool from what we desire, that is a genuinely autonomous system. We all know that in 2026 the iteration cycle for state of art models has compressed to roughly 35 days, and the base models are yielding diminishing returns. Hence, the real competitive advantage has shifted to what surrounds the model, and nothing surrounding it is more consequential than memory. Every LLM that you have ever interacted with is at its core a stateless function. That means input goes in, output comes out, and model retains nothing. So that means that every session actually begins with a blank slate. And this works quite fine for single turn tasks, which might be simpler tasks. But it fails catastrophically for anything autonomous, which includes something like multi-step planning, evolving goals, iterative workflows, or long horizon collaborations. And this evolution from stateless inference engine to persistent cognitive agent is the defining transition of the current moment in AI. And memory is the bridge that is making that transition possible. Without memory, agents are not agents, they are simply sophisticated autocomplete functions. Let's look into the cost of statelessness. So, for long horizon planning, the agent is not able to track what actions it has already taken, and it loops or contradicts itself. It also prevents adaptation because agent cannot remember a particular strategy has failed, and so it repeats the same mistake again and again. It is not even able to collaborate with other agents because it cannot recall what it has shared with other agents in past, and so team fragments. So in general, context window helps, but they are finite, expensive to fill, and every time session ends, it resets completely. So in this sense, stateless agents have a hard ceiling, and that ceiling is the context window. And for any genuinely complex task, we have already hit it. Agent memory is basically a mechanism that stores, indexes, and retrieves information across time, or even across agent boundaries to support future reasoning and action. And here the key phrase is across time. So it is not just about fitting more tokens into prompt, rather it is about persistence. And a system with true agent memory can be shut down and restarted, and it will be able to pick up from where it left off. It can incorporate new facts without forgetting older ones. It can also learn just by doing things rather than requiring retraining. So this capacity basically transforms a static parameter set, which is basically all that base LLM is, into a dynamic system capable of genuine evolution. So let's try to understand the difference between agent memory and RAG. RAG, which is retrieval augmented generation, and it is often conflated with agent memory, but actually these two are quite different. RAG is just a pipeline. You retrieve document, You inject information into prompt and then generate a response. So in that sense, it is stateless. It does not persist. It does not learn, and it does not update based on the agent outcomes. On the other hand, agent memory is a cognitive state. That means it accumulates, evolves, and reflects on the agent's lived experiences. So the way to think about the difference is that RAG is just a library you consult, whereas agent memory is the knowledge you have internalized and continue to build through practice. So one is just a lookup while other is genuine learning. Let's now look into how agent memory is different from LLM memory. So ML researchers and hardware engineers sometimes use memory, which might mean attention KV cases or GPU bandwidth or even in-weight knowledge. So this is not what we mean by agent memory. Agent memory is basically an architectural design choice that we have at application layer. So it is basically a deliberate system designed for managing what agent knows, when it accesses it, how it updates it, and even how it forgets it. Agent memory can span databases, graphs, embedding stores, parameter modules. It can operate over in minutes, sessions, days, and even years. So conflating the hardware memory or model weights basically obscures the real engineering challenges. And this is why, we have situations where architectures do not actually achieve true persistent cognition. So in order to build an agent with cognitive continuity, we need to answer three design questions all at once. So what is the structure should the memory take? What is the purpose that memory will serve? And how we want the memory to evolve over time. And these are not independent questions because the structure you choose will constrain the functions it can serve. And the functions you need drive the dynamics you must support. So designing cognitive continuity is not just about picking the best available vector database. It is rather about designing a coherent system that will hold together during the entire life cycle of agent's operation. So in that sense, it is more of a system design problem and not just an ML problem. In order to understand agentic memory system, we'll be looking into three orthogonal dimensions in this talk. The first being forms, which means what is the physical or representational structure of memory? Is it token level text, model weights, or is it continuous embedding? Next, we'll look into functions. So what is the cognitive purpose that the memory is serving? Is it for grounding in facts, accumulating experience, or managing immediate context? And finally, we'll look into dynamics. So how is agent memory operating over time? How is it formed? How does it evolve? How it's retrieved? So for building an agentic system, it is important to understand all these three aspects. So historically, we have used very crude binary categorization, short-term versus long-term memory. But these labels basically obscure more than they reveal. For example, both a knowledge graph and a rolling text summary are both long-term memory. But then they have a completely different storage cost, retrieval mechanism, editing properties, and even failure modes. Hence, the unified form, function, and dynamics taxonomy that we want to use is quite necessary in order to design memory systems that are composable, interoperable across agent implementation, and measurable against well-defined benchmarks. And hence we can say that precision in this taxonomy is almost a prerequisite for precision in engineering. So before we dive further into the technical details, our central premise is that agent memory is prerequisite for everything that makes such an AI agent genuinely autonomous, whether it is sustained reasoning, adaptation, personalization, or lifelong learning. So without it, the ceiling is context window. But with agentic memory, the ceiling rises to what agent has experienced and learned. So from here on, every slide that we'll be looking into is basically building the technical vocabulary and the conceptual foundation that is required for designing such a ceiling breaking system. So let's go forward. We begin part 2 by asking the most fundamental structural question. That is, in what physical or structural form does the agent memory actually live in? And the answer is not a single architecture. Rather, it is a spectrum. And choosing the wrong form for the job basically breaks down everything downstream. The structure of memory store is not just an implementation detail. Rather, it is a design decision with direct consequence on different factors like latency, editability, or reasoning depth. So basically, a flat text buffer or a knowledge graph both will answer completely different questions, even though they technically store the same facts. So memory form basically defines the bounding box of agent capability. And if we choose the wrong form, then no amount of retrieval engineering will basically compensate for that. So memory can be stored in 3 core forms. It can be token level, parametric, or latent. So token level memory is just explicit and editable tokens stored as discrete inspectable units. On the other hand, parametric memory is basically embedded directly inside the model weights, and hence it is implicit, fast, and has zero retrieval latency. Latent memory basically sits in between these two, and it is living in hidden states such as KV caches or continuous embedding. Hence we can say that each of these has a genuine non-overlapping strength, and each serve as a different part of our cognitive stack. Let's look into token level memory. So it is stored as a persistent inspectable units such as text, visual tokens, audio frames, structured JSON, or knowledge graph triplets. And because these units are visible and external to model, they are fully auditable, easily edited, and straightforward to route or share across agents. And this transparency is basically its superpower. Now, there are systems like MemGPT or Mem0 which are built entirely on this foundation. Even in production deployment, token level memory is also easiest to govern. You can read it, correct it, delete it, as any human operator would do without retraining anything. So tokens can be stored in different manner. The first can be flat memory or 1D text buffer. Here it is accumulated just like a sequence or bags of discrete units with no explicit topology between records. And we can think of this as dialog logs or episode trajectory pools or vector databases of text chunks. Here, retrieval is basically via similarity search. And the advantage of such a system is that it is very simple and easy to scale. You can simply append or prune at minimal cost. But at the same time, there's the weakness that the flat memory has no internal semantics about how records relate to each other. And because of this, as the store grows into millions of entries, the compositional reasoning suffers because there is no structural backbone to navigate. Next, we have planar memory or 2D graph structure. So planar memory basically introduces explicit relationships between units within a single layer. It can be trees, relational tables, or graphs. We have systems like AMEM, which organize memories as a card-based linked nodes, or HippoRAG, which models memory as an open knowledge graph. And this planar memory is nothing but knowledge graph connecting entities and their relations. And this relational structure basically enables multi-hop retrieval and richer contextual grounding. But at the same time, the construction and the search cost is higher as compared to flat approaches. At the same time, the schema design choices that we make have long-term consequences. Next, we have hierarchical memory stack with multiple layers and cross-layer connection. Here we have raw observations at the bottom, then we have compact summaries in the middle, and high-level thematic pattern at the top. For example, we have GraphRag, which builds community detection hierarchy from document entry graph. And because of this, we can have fine-grained fact lookup as well as broad thematic retrieval from a single architecture. Similarly, we have HiAgent, where the completed sub-goal trajectories are compressed in summaries, whereas active sub-goals are kept in full detail. So what we can see that this vertical abstraction is what gives the cognitive powerful form. But then maintaining this coherence across different layers is quite challenging and computationally demanding. So we have looked into token-based memory storage. Now let's look into the next, that is parametric memory. It has no external storage. Information is encoded as statistical pattern directly within the model weights. And when model recalls a fact, it is retrieved through the forward pass itself. It's not fetched from external database. So this makes it extremely fast. There is zero retrieval latency and also consumes no context tokens. But then there is a downside. Once we want to update the parametric memory, we need to retrain or fine-tune it. Also, there's a risk of catastrophic forgetting. And at the same time, its contents are opaque, so we cannot inspect what model knows. So parametric memory can be internal or external. So in internal parametric memory, we do full fine-tuning or continued pre-training and model editing. For example, Rome uses causal tracing to pinpoint exact MLP layer that encodes any specific fact and then applies update to inject corrected knowledge. Another approach, MEMIT, extends it to batch editing, where it can update thousands of facts simultaneously. So these methods are powerful for injecting domain knowledge at deployment time, but then the edit itself has a training cost associated with it. We also have external parametric memory, which adds modular parameter sets alongside frozen base model. So LoRA adapters and systems like WISE, Elder They maintain a dual memory architecture where pre-trained knowledge and newly edited knowledge live in separate parameter space. And there's a routing mechanism which selects between them during the inference time. So this is basically best of both worlds. You update memory without touching the core weights, and adapters can be retrained, swapped, rolled back, uh, and we also mitigate the problem of catastrophic forgetting. So in production setting, this is quite a standard approach for domain specialization. Next, we have latent memory, which lives in models' internal representational space, such as KV cache, hidden state activation, or continuous embedding vectors. Thus, it is not human readable, but it preserves fine-grained contextual signals. We do not have to make any external database call as the memory is woven into the computation itself. So latent memory is high density and avoids all external I/O overhead. KV cache reuse is one of the most practical forms of latent memory. So we store and replay the attention key value pairs from prior computation instead of reprocessing the same context from scratch at every turn. And the savings are dramatic. These techniques can reduce the effective context length by 50 to 80% with minimal degradation. And at production scale with thousands of agents, the savings are huge, both in terms of time and money. Next, we have generative latent memory, where we create entirely new compact representations on demand rather than reusing existing computation. For example, autocompressor trains models to encode long documents into small set of summary vectors that act as soft prompt for downstream reasoning steps. These basically encode information that cannot fit in any raw context window while avoiding overhead of token level storage and retrieval latency. So we have looked into the three different modalities for representation. Token level memory wins on editability, auditability, and operator control. You can read, correct, and delete it. When it comes to parametric memory, it wins on integration depth and zero latency recall, as the knowledge is baked in. And then we have latent memory, which wins on information density and efficiency. So a serious production system will use a combination of all the three and routing different type of information to the form that serves it best. And if we have a monoform architecture relying on only one of these, then we will always leave, performance, flexibility, or auditability on the table. So the key takeaway from part 2 is that memory form is not a neutral implementation choice. Rather, it determines what reasoning the agent can and cannot do. So if we are in a high stakes domain requiring audit trails, then we need token level memory. If we are in a low latency inference pipeline, we require parametric or latent form. For long horizon multi-hop reasoning, we need hierarchical topology. So there is no single right answer. An agentically intelligent system will be multiform by design. And the routing logic needs to be intelligent enough for any mature system. In the last part, we learned about what carries memory. And in this part, we look into why do agents need memory at all. Now we ask the question, why does a goal-directed agent need memory? The answer is not simply to remember things. Memory serves distinct cognitive functions, and confusing these functions leads to architectures built to solve the wrong problem. So there are three primary functional pillars for persistence. We have factual memory that answers what does the agent know. So these are verifiable facts, world states, user profiles. Then we have experiential memory, which answers how does the agent improve. So these are the strategies, outcomes, skills extracted from past runs. And then we have working memory, which answers what is the agent processing right now. These are the active task buffer managing immediate context. So all these three are not redundant. They operate on completely different timescales. From milliseconds to sessions to lifetimes. And conflating these produces systems that are mediocre at all three. Factual memory stores verifiable, explicit facts about the users, the world, and the environment. In agents, it functions as the persistent knowledge base, ensuring that the system remembers user preferences, domain constraints, and environmental states across sessions without re-eliciting them each time. This enforces three critical properties. First is identity consistency. The agent knows who it is talking to. Second is contextual coherence. The agent's world model is accurate and current. And personalization. That is, the behavior is appropriately tuned towards the individual. So factual memory in turn is the ground truth layer of the agent's cognition. So we have user factual memory that specifically tracks identity, preferences, historical commitments, and interaction patterns for a specific person over time. So systems like memory bank index interaction history with timestamps and build evolving user profile that survive session boundaries. The goal is behavioral consistency across interaction. An agent should never ask for your name, preference, or context a second time. More deeply, it should notice when your preferences change and update its model of you accordingly. And this is what separates a chatbot from a genuine cognitive partner that makes interaction meaningful and more effective over time. Next, we have environment factual memory, which covers everything external to the user. So something like documents, code bases, tool states, API schema, shared knowledge bases, and actions of other agents in the system. For example, HippoRAG models this as a structured knowledge graph, enabling multi-hop evidence propagation. MetaGPT and GameGPT use shared message pools as centralized world state for multi-agent coordination. When one agent discovers a fact, then every agent benefits immediately. And without a shared world model, every agent in the team reconstructs the same environmental representation, independent. So the collective intelligence is permanently capped at the intelligence of a single agent operating alone. Experiential memory is where agents stop being brittle and start being genuinely capable. So rather than just storing facts, it stores outcomes of doing things. So successful workflow, failed plans, extracted heuristics, executable procedural skills. So in one way, this parallels human procedural and habit memory. So the critical property here is that experiential memory enables an agent to improve across episodes without any parameter updates. So it is a non-parametric path to continual learning. You accumulate operational wisdom purely through experience and not through retraining. So you will see that agents with rich experiential memory will outperform naive agents even when both of those are using the same base model. The simplest form of experiential memory is raw trajectory storage. That is the full sequence of states, actions, and outcomes from past episodes. For example, reflection stores both the interaction trajectory as short-term memory and self-generated verbal feedback as long-term memory. The agent publicly reflects on its own failures and stores those reflections. Jarvis 1, on the other hand, stores successful Minecraft survival experiences as plan environment pairs for direct retrieval. So the benefit is high information fidelity. That is, the agent can literally replay a past solution. But then the weakness is that raw trajectories don't generalize well across novel contexts. And storage cost also goes quite significantly. To overcome the limits of raw trajectories, strategy-based memory distills transferable abstractions. For example, buffer of thought maintains a meta buffer of thought templates, generalizable cognitive skeletons that can be instantiated for new problems. We have agentic workflow memory, which extracts reusable navigation patterns from web interaction histories. H2R, on the other hand, introduces two-tier reflection. High-level planning insights extracted from full task outcomes, plus stepwise sub-goal insights from intermediate checkpoints, thus capturing both forest and trees. These abstracted patterns apply to novel situations where no exact trajectories match exists, enabling genuine cross-task generalization from accumulated experience. Working memory is agent's real-time cognitive workspace, a bounded, dynamically managed buffer for current tasks. In LLMs, the context window serves this function passively. Whatever fits stays, whatever doesn't is excluded. But for a true agentic working memory, we require active management, deciding what enters the buffer, what gets compressed, and what gets evicted. Without this, long-running agents will accumulate context pollution, will have noise, contradictions, and resolve subproblems that will actively harm reasoning quality for current tasks. Let's look into context management. So in single turn setting, working memory does input condensation, compressing a long document into dense task relevant representation before reasoning begins. For example, LLM Lingua estimates token level perplexity to discard predictable low information content. In multi-turn setting, the challenge is temporal. The agent must maintain a running cognitive state across many interactions. For example, Mem1 uses reinforcement learning to train a summarization policy, and it produces a continuously updated internal state. So that way it is effectively optimizing the compressor itself through downstream task reward. So that way summarizer learns what to keep while observing whether the compressor choice led to correct outcomes. The three memory functions form an interconnected loop, and routing between them is a critical engineering problem. For example, factual memory must be loaded into working memory to ground the current task. Similarly, experiential patterns must be retrieved as planning scaffolds whenever it's relevant. At the same time, completed working memory episodes must be distilled into factual and experiential stores before being evicted. So we have systems like MemOS which implement this orchestration with a mem scheduler that dynamically selects among parametric activation and plain memory based on user, text, and organizational context. So here we have routing intelligence, which is meta-intelligence. The agent must model its own knowledge topology to navigate it efficiently. Memory architecture is not universal. It basically follows domain logic and operational constraints. For example, for code generation agents, we need tight experiential loops, tracking which API calls failed, which refactoring pattern succeeded, which test strategies generalize. On the other hand, if we have customer service agent, then that is dominated by user factual memory, every past interaction, contractual commitment, and support ticket matters. If we have scientific research agent, then we need deep world model memory to avoid revisiting already explored hypotheses, because the intellectual waste of duplicated effort would be catastrophic. So the cognitive architecture that serves in one domain may actually harm in another domain. For agent memory, forgetting is a feature, not a failure. For example, the FadeMem architecture, which is inspired by Ebbinghaus' forgetting curve, it implements adaptive exponential decay on memory strength. Every memory entry's retention strength is modulated by semantic relevance, historical access frequency, and elapsed time. Entries that remain unaccessed or semantically isolated decay below a deletion threshold and are permanently pursed. On the other hand, entries that are frequently accessed exhibit superlinear retention and are promoted to durable long-term layer. In empirical evaluation, FadeMem retains 82.1% of critical facts while using only 55% of storage of native infinite retention system like MemGPT. So selective forgetting is not a loss. It is basically compression towards relevance. Persistent memory introduces a failure mode that stateless LLMs don't face. False recall. An agent can retrieve a stale user preference, an outdated fact that was once correct, or a trajectory pattern from a subtly different context, and act on it with full confidence. This risk is compounded by memory poisoning. If an adversarially crafted document contaminates the agent's semantic or episodic memory store, that corrupted memory can silently influence future reasoning long after the initial explosion. The lethal trifecta for agentic system is first, access to sensitive data, second, exposure to untrusted content, and third, autonomous action capability. All three together can create catastrophic compounding risk. We have looked into three functions which serve three distinct cognitive purposes. Factual memory grounds the agent in a stable, accurate world model. Experiential memory enables agent to learn from doing without retraining. Working memory keeps the agent focused and coherent in the moment. The art of memory architecture is wiring these three systems together into a seamless cognitive loop. Factual memory informs working memory. Working memory generates experience. Experience refines factual memory. And the cycle improves the agent continuously across its operational lifetime. In part 2 and 3, we looked into the static picture of agentic memory, what memory looks like, and what is it for. In this part 4, we'll be introducing a new dimension to the agentic memory, that is time. So memory may not just exist, it must form, evolve, and be retrieved dynamically as agent operates. And this is what makes agent memory different and makes the system cognitive and not just be a simple database. So the full memory life cycle of agent is continuous three-stage cycle. It starts with formation, where new knowledge is extracted from raw experience. Then we have evolution, which integrates, refines, and prunes the knowledge base as the world changes. And finally, we have retrieval that accesses right knowledge at right time in order to support reasoning. And this reasoning outcome is then feedback into formation and evolution, thus creating a genuine learning loop. So this is quite important because an agent that cannot close this loop will most probably plateau at its initial knowledge state. At the same time, an agent that can close it will compound improvement indefinitely without requiring parameter update. So memory formation is a process of transforming raw interaction data, which can be dialogues, trajectories, video frames, tool call outputs, and we transform it into compact, actionable knowledge units. The naive approach would be logging everything verbatim. But then intelligent approach is to select extraction, identifying pattern that will have long-term utility and discarding transient noise. And we have 5 formation strategies. We can be semantic summarization, knowledge distillation, structured construction, latent representation, and parametric internalization. And we have briefly looked into these earlier. So each operates at a different granularity and produces qualitatively different kind of knowledge artifact. So knowledge distillation basically extracts specific cognitive assets from raw data. So facts, strategy, workflow, heuristics. For example, for factual memory, system like Think in Memory converts dialogue turns into abstract thought representation, which are high-level declarative summaries, and thus preserving long-term personal coherence. For experiential memory, Expel contrasts successful and failed trajectories, and thus extracts holistic planning insights across both. S2R, which is a two-tier reflection system, produces both high-level planning insights from full task outcome and stepwise sub-goal insight from intermediate trajectory segments. So this binary granularity basically captures both strategic lessons and tactical details. So this is how raw experiences become reusable intelligence. So while formation extracts knowledge, evolution then integrates it. So we cannot simply append new memories into existing store. There can be cases where these ignore semantic dependencies or create contradictions or result in unbounded growth. So agentic memory is handled using 3 operations: The first is consolidation, which merges and abstracts new with existing memories in order to generate higher level insights. Then we have updating, which resolves conflicts when new facts contradict old ones. And finally, we have forgetting, which removes low value or outdated entries. So these three mechanisms actually keep the memory store coherent, accurate, and manageable as our agent accumulates ever expanding history of experience. So we also need to handle contradictions properly. Let's say a user has moved to a new city. So the factual memory stored now will contain two conflicting home addresses for the user. So agent must detect this and resolve it correctly. So we have system like DSmart, which encode facts as knowledge graph entries, and they trigger update operation the moment contradictions are detected. Another system, JEP, introduces a more sophisticated approach. They use temporal soft delete. That is rather than hard deleting old facts, it marks them with invalid timestamp, thus preserving historical context while ensuring that the current queries answer correctly. So this is more robust than destructive replacement. In some domain, it is quite important to know what has changed and when things have changed. That itself is a valuable information. So consolidation basically transforms these fragmented short-term traces into coherent long-term schemas. So we have local consolidation, which merges highly similar memory fragments into nearly identical knowledge graph entries that collapses into one richer record. Then we also have global integration as demonstrated by Matrix. So it performs holistic optimization across full history of execution trajectories and reflective outputs, thus producing task agnostic principles that will transfer across a wide range of feature scenarios. We also have frameworks like EvoSC that automates this entire process. So in addition, we also need to have proper retrieval strategy. A perfectly curated memory store is useless if agent retrieves wrong piece of information at wrong moment. So retrieval itself is a four-stage pipeline. First, we need to decide when and whether to retrieve information at all. Then we have constructing an effective query that is aligned with the memory index. Then we execute search across the memory repository. And finally, we post-process raw result into coherent, non-redundant context. So each of these stages has its own failure modes, and each has specialized mitigation strategies. So retrieval is as important as memory structure itself. Next, let's look into lookup. So we use dense semantic retrieval, which encodes both queries and memory entries into shared embedding space, and then retrieves using cosine similarity. This is the default retrieval approach in most agentic frameworks. MemGPT, Memory Bank, AMEM, Voyager all rely on it. And the strength is semantic generalization. You do not need exact keyword mass, you just need some conceptual proximity. The weakness is that in forced top K retrieval returns a fixed number of results, regardless of relevance quality. And then we can also have semantic drift, which can basically distract rather than help. So in modern system, we pair semantic retrieval with re-ranking module, which basically filters this noise before injecting result into the prompt. Next, we can use graph retrieval, which leverages explicit topological structure. So walking edges to resolve multi-hop logical dependencies that simple vector similarity cannot capture. So HippoRAG, for example, seeds personalized page rank on retrieved seed entities and then ranks the rest of the graph by proximity, thus enabling multi-hop association that purely similarity search misses entirely. We also have CAM that uses LLM to steer subgraph exploration by selecting informative neighbors of the central node. Then Adaptive Memory Framework introduces a dedicated query routing agent that determines the retrieval granularity, escalating from coarse executive summaries to high resolution episodic log. So most sophisticated agents route retrieval strategy dynamically based on context. For example, Agent RR switches between procedural templates and experiential abstractions based on real-time environmental feedback. Next, we have MemOS, which implements Mem scheduler, which is rebuilt on Redis string that selects between parametric, activation, and plain text memory based on user, task, and organizational context, with queue isolation and automatic recovery. Then we have HMem, which adds cores to fine hierarchical routing, moving from domain to category to episode layer before narrowing to the most relevant submemory. So thus dynamic routing is a meta-intelligence. The agent models its own knowledge topology to navigate it efficiently. In production deployment, every millisecond counts. So retrieval adds latency before the first token is generated. So we have Pancake Memory Library, which is designed for GPU accelerated multi-agent deployment. It implements multi-level index caching with coordinated acceleration protocols. It achieves 20x, 26x throughput improvement over unoptimized baselines. At the hardware level, we have Hippocampus system that uses compact binary signature and dynamic wavelet matrix. This helps in scaling linearly with memory size. So actually the engineering problem of memory latency is as consequential as the research problem of memory accuracy. The most effective latency optimization is avoiding retrieval entirely for commonly needed information. Say for example, if a customer service agent retrieves the same company policy document 80% of the time, then that document belongs in KV cache prefix, which should be preloaded at session start, not refetched on every turn. So we also have predictive cache trees. They preload branch of likely retrieval paths before they are needed, based on task types and historical access pattern. So this in turn shifts the retrieval bottleneck from runtime to prefetch time, enabling real-time agent responsiveness at production scale without sacrificing the breadth of available memory. Retrieval quality is not just a structural problem, it is also a learning problem. For example, memory R1 applies reinforcement learning to train extraction module that learns what memories to surface and how to prioritize them. It is optimized through reward signals tied to downstream task performance. Next, we have MEMAlpha, which frames memory updating as a policy learning problem, training the agent to decide when, how, and whether to update its own memory store. Next, MIRAS learns attentional bias over historical memory based on novelty and surprise factor of incoming information, thus prioritizing salient anomalies over predictable routine data. So when retrieval and update decisions are learned rather than heuristics, the system continuously improves its own memory quality. So the central insight of this part 4 is that memory is not a static artifact. It is rather a living process. Formation, evolution, and retrieval run continuously throughout the agent's entire operational lifetime. A robust memory system mirrors neuroplasticity. It strengthens frequently used pathways, weakens unused ones, resolves conflicts as they emerge, and synthesizes new schemas from accumulated experience. Static records permanently cap potential, whereas dynamic memory replaces the ceiling with a trajectory. And the trajectory points upward indefinitely as long as agent continues to act, observe, and learn. So we have built the complete conceptual framework, forms, functions, and dynamics. This part 5 connects it to the present and looks into the future. The production infrastructure where these ideas are being deployed today, and the research frontiers where they are heading. The abstract taxonomy that we covered lives inside concrete engineering system. As of 2026, the agent framework is the entity that manages how memory is structured and accessed. LangGraph defines agent workflows as cyclic directed graphs. Every agent node, tool call, memory retrieval operation is typed, inspectable graph transition. This gives engineers explicit control over state management and error recovery. On the other hand, frameworks like AutoGen and CrewAI take a conversational multi-agent approach. Agents with distinct persona and memory access rights collaborate only through natural language delegation. This helps them excel in open-ended scenarios where solution path is not deterministic. We also have Llama Index, which specializes in document-heavy knowledge work with deep vector store integration. Semantic kernel, on the other hand, bridges enterprise SEO deployments. So the critical insight is that the framework, not the model, owns the memory architecture. And switching base models should not require you redesigning the whole memory infrastructure. So a parallel infrastructure layer has emerged to answer a deeper question: who manages the memory store itself? With this, let's look at memory operating systems such as MemO, Letta, that was formerly MemGPT, and MemOS. These decouple memory management entirely from both the foundational model and the orchestration framework. For example, MemOS v2 organizes knowledge into memory cubes backed by Neo4j graph databases for structured relation and QRANT vector databases for semantic retrieval, giving operators full inspectability and semantic search at the same time. Natural language memory editing via MCP allows both human operators and agents themselves to deprecate obsolete fact through plain language instructions. The decisive architectural advantage is that when you upgrade your base model from one provider to another or to a next generation version, the agent's accumulated memory, behavioral persona, and procedural skills remains intact. The cognitive state survives the model update. You cannot improve what you cannot measure, and measuring agentic memory correctly is substantially harder than measuring static model performance. Traditional benchmarks evaluate single turn accuracy. Agentic memory benchmarks must measure temporal coherence across simulated months of interaction, multi-hop reasoning accuracy across large memory stores, and forgetting efficiency, whether the system correctly discards stale information and retains what matters. Long-term interaction benchmark simulates 30 days continuous interaction and tests resistance to memory drift. SWE-bench for software engineering and OS World for operating system navigation assess fully grounded action execution, measuring whether the agent's world model tracking is accurate enough. These benchmarks are defining what's good memory actually mean for production at scale. The three-dimensional taxonomy that we have just looked at form tells us how memory is stored. We have token level, which is explicit, editable, auditable. Then we have parametric, which is implicit, fast, and integrated. And latent, which is dense, efficient, and private. Next, function tells us why memory is needed. Factual grounding for world consistency. We need experiential accumulation for competence growth and working memory for task focus. Then dynamics tells us how memory lives over time. Formation from raw experiences, evolution through consolidation and conflict resolution, and retrieval mass to movement. These dimensions are orthogonal. Any memory system can be analyzed across all three, and gaps in any one dimension produce predictable failure modes. The next architectural frontier actually removes the human engineer from the memory schema design loop entirely. So today, when we are building a production memory system, it requires extensive hand design, what to store, what schema to use, when to expire entries. Self-organizing systems like MemOS and EverMemOS point towards a future where agents autonomously compile and govern their storage topologies from observed task patterns. The Stardust paradigm of MemOS treats memory as crystallization process. Structure emerges organically from agents' accumulated experience rather than being pre-designed. When an agent can build and maintain its own architecture, the bottleneck of human schema design largely disappears. RL and memory have profound natural symbiosis, and we are just beginning to exploit it. Memory provides episodic experience replay that stabilizes RL training across environment, preventing catastrophic forgetting between training domains. RL provides the reward signals that teaches the memory system which experiences to extract, prioritize, and retrain, thus closing the loop between action and remembering. MIRAS operationalizes this. It learns additional bias over historical memory based on information surprise, making the memory system itself an RL optimized component. When the agent learns not just what to do but what to remember, every action simultaneously improves task performance and memory quality. This is the engine of genuine compounding autonomy. The real world is not text. The embedded agents must remember visual scenes, spatial maps, audio cues, sensor streams, and their temporal relationships simultaneously. For example, MemOS builds multimodal hierarchical knowledge graphs that unify text, image, video in a shared memory structure. Karma manages 3D scene graph information in long-term memory alongside dynamic object state in short-term memory. Video Thinker gives agent procedural memory tools, temporal retrieval for scanning video transcripts, and temporal zoom for drilling into specific intervals. The frontier challenge is temporal synchronization. Different modalities arrive at radically different sampling rates, and the memory system must maintain a coherent cross-modal representation across these heterogeneous timescales. When agents share an environment, the memory becomes coordination substrate, not just a personal resource. The fundamental topological choices are: we can have local, so that we have isolated stores, message passing coordination, zero contention, but high redundancy. Or we can choose shared, so that we have centralized pool, zero redundancy, but high concurrency complexity. Or else we can even have hybrid, where we have fast local caches for working memory and governed central repository for verified long-term knowledge. For example, the adaptive memory framework implements a dedicated refresher agent that continuously audits the shared pool, purging obsolete entries and resolving inconsistencies in the background. The shared memory pool architecture for transformers embeds distributed memory slots directly at transformer level. So real-time swarm coherence at scale remains one of the hardest problems in this space. Persistent self-evolving memory introduces security and alignment risks that stateless LLMs simply don't face. The lethal trifecta defines the critical risk zone: an agent that has access to sensitive enterprise data, is exposed to untrusted external content, and can execute autonomous actions. In this zone, memory poisoning attack is not a transient exploit, it is a persistent backdoor. An adversarial instruction embedded in past web page enters the agent's semantic memory and silently conditions future unrelated reasoning sessions. Hence, the defenses must be structural, cryptographically signed audit logs for every memory read and write, zero trust role-based access control with minimum necessary memory access, autonomous self-audit controllers that cross-reference retrieved memory against policy constraints before any action is taken, and TTL expiration on high-risk memory entries. Safety is not a constraint applied to memory from outside. It must be designed to live into the formation, evolution, and retrieval life cycle. Memory is not a supporting feature of AGI. It is the definitional prerequisite. Every conception of general intelligence requires continuity of self across time, the ability to accumulate experience, build on prior knowledge, maintain a coherent world model, and improve from interaction with diverse environments. Without persistent, self-evolving memory, an agent cannot do any of these things beyond the boundaries of a single context window. So the formal taxonomy we have built, form, function, and dynamics, give us a precise map of exactly which architectural capabilities remain to be solved. The distance to AGI is not a mystery. It is measurable, and memory engineering closes most of it. We are at an inflection point. Memory has crossed the threshold from optional enhancement to first class architectural primitive, as fundamental as the inference engine itself. Enterprise software built over the next decade will be defined by the sophistication of its memory architecture, whether agents can remember across sessions, learn from accumulated operations, and serve individual users with genuine personalization. The base model arms race is slowing, and the memory operating system race is accelerating. Every major AI deployment going forward will be differentiated not primarily by which model it uses, but by how intelligently it manages the agent's cognitive state over time.